record. Oh, what can I say? All right. From all the observations, this is something that takes a long time for people to come up with. So in order for you to fully understand motion, there is another law called Newton's third law of motion. All right? Newton's third law. Oops. This one. This is a very peculiar law. You need it for conceptual understanding, and you need to know how to apply that correctly. Now, this statement actually is sometimes not accepted by people because they find it very difficult to accept. But if you really try to analyze the situation and say, how do I understand what happens? Then you're forced to this conclusion. Okay? That's just the easiest way. You may come up with a very, very complicated way of doing it. You are welcome to try to understand motion in a different way than this. What we do know is that this works for all the observations that we can come up with in a lab when you make all kinds of measurements to verify it. I'm not saying this is the only way. Maybe you can come up with a better way. In fact, physicists have come up with better ways of looking at things. We will touch upon them, looking at it in terms of energy, but in more advanced physics, we've got other ways of looking at it, but that is just farther out there. Okay? So what is this third law? The third law says, whenever objects interact, for you, interaction may mean coming in contact, collision, when they collide with one another. Okay? Now, it turns out that you hear about planets colliding or stars or galaxies colliding. They don't come together and be in contact. You can have collision where you don't come in contact as long as they exert forces on one another. That's the important thing. Exerting forces influences one another. Now, in all the experiments, it turns out that there is this law that summarizes all those interactions. And what it says is that forces, when objects interact, forces always come in pairs. All right. The key thing is these pair of forces, pair means two, right? These two forces always act on different objects. We call one action reaction. If you want, if I go to a bee's nest and I smack it, that's my action. What's the reaction? All these bees come after me, right? That's the consequence. Now, when we talk about forces, I mean, you do something, you act on an object. It turns out that whatever you do to the object exerts a force back on you. This force is equal in magnitude and opposite in direction. So if I push against the wall with 10 Newtons of force, see, I'm pushing on the wall, 10 Newtons of force. What Newton's third law tells you is that the wall pushes back on me with a force that is in the opposite direction. So I push that way, the wall pushes in the opposite direction. And what is the magnitude? If I exert 10 Newtons, it exerts 10 Newtons. If I push with 100 Newtons, it reacts back with 100 Newtons. And this is true no matter what the motion is, right? The wall doesn't move. If I push on it with 10 Newtons, I say the wall pushes back with 10 Newtons. Everybody seems to agree with that. But if I, take this pen, right, and I say I'm going to push on it with 5 Newtons of force, and you see I'm forcing it to move. It's accelerating now. I push on it with 5 Newtons of force. Guess what? The pen pushes back on me, also with 5 Newtons of force. That's the part where people don't seem to agree with it. It doesn't make sense. But if you actually analyze it, the only way you can understand why things move the way they do is to accept that that is the reality. I don't care what happens. If I push on you with 5 newtons, you push back on 5 newtons. I may be pushing you all the way to, wherever, off the cliff, doesn't matter, right? The fact is, action-reaction pair, me pushing you and you pushing back, always equal opposite forces. And the key is they're on different objects. I exert a force on you. That's my action force. You exert a force on whom? On me. Okay, not on yourself, not on the man on the moon, not on this box, on me. Action, reaction are pairs of forces that are oppositely directed and equal in magnitude on different objects. That's something you have to remember. So we call this action-reaction pair. Now that you're armed with this knowledge, you can rest assured that if you meet a bully who punches you and you feel really painful, you don't have to retaliate. You say, whatever you hit me with, I hit you back exactly the same magnitude. Right? It's true. It is true. It's just that he hit you on the soft spot and you bleed. But okay. So let me give you some examples. There are several here. This one is very easy to understand, or easier to understand rather, right? And you have a fridge, you have a heavy fridge, and you want to move it. Now, if you push on it with 55 newtons to the right, that's the action, that's the force exerted on the fridge. The fridge exerts a force back on you. And they write it as minus F vector, because the minus F vector is just to indicate to you that it is a vector with a magnitude same as F, but in the direction opposite to F. That's how you mathematically write down Newton's third law, the consequence of Newton's third law. I exert vector F, the reaction is minus F. Okay? That's easy to understand, just like this. This one, if the fridge is not moving, everybody accepts it. Push with 100, fridge not moving, the fridge is pushing back with 100. This one, you are resting on something that's frictionless. Whatever you exert on this, it starts accelerating. This is the force F, right, acting on this object. If I ask you, what is the acceleration of this object? You say, by Newton's second law, I know the magnitude of the force F. I divide by the mass of this, I'll get the acceleration of this. I don't care that the object is exerting a force on the hand. That is not in the statement of Newton's second law. Newton's second law says, which body are you interested in? That one? Okay, we look at that body. The fact that that body is exerting a force on that body is immaterial. All you care about is what forces are acting on that body. What force is acting on this body. There can be several forces. Then you do a vector sum. Okay? Now, this one, you have the space shuttle. Like I said, you do not need contacts. Gravitational force is one where you'll feel the influence even though there's no touching. Okay? The space shuttle on above is attracted by the Earth. So there's a force downwards on it. That's the action. What is the reaction? The reaction is what? The space shuttle would exert a force on the Earth. The Earth pulls down on the space shuttle pulls up on the Earth. Okay, this way. See, the force on the Earth is upwards. They are mutually attractive. There's nothing you can do. If I exert a force on something, it would exert a force back on me. And there's just no way around it. That's actually how you know that there's something in the way. No, I'm exerting a force. If there's nothing opposing it, I don't feel it. How do I feel it? When I slap something, that something slaps back. I feel the pain in my hand. That's the force, the reaction force. That's how I experience it. Now, for the car, this is a little bit getting used to in a sense. When you turn the engine, the pistons fire, it rotates the wheel, okay? So the wheel wants to rotate this way. Now, if you have experienced this on the sand or in mud, you would know that when the wheels are turning, what direction is the mud in throw? This way, right? In other words, it's just telling you, it's showing you that the wheel is exerting a force on the ground, pushing it that way. That is not the force propelling the car. Newton's third law says, car, you push on ground, what does ground do? Opposite direction. So you see the car, the wheels are pushing the earth in this direction, the earth pushes in that direction. That's why your car accelerates in that direction, because that's the force exerted on the car. If I want to know how the car is accelerating, I need to know the force on the car, not the force that the car exerts on the earth. That is immaterial as far as the motion of the car is concerned. Yes?
What makes the earth one, like, what, reach, like, point to each other, except, like those, they face, opposites, right? If you push something, push back, but on that one, why?
This one?
Yeah.
They're both opposite. I mean,
Oh.
when you draw this, right, this is the force on the car. I mean, on the earth, right? This is the force on the car. This is the force on the fridge. This is the force on you. They're all opposite to each other.
Oh, okay. So they're all of them are.
Yeah, you see, this is the force on the space shuttle. This is the force on the earth. If you imagine them touching, then you can move this arrow down, this arrow up. Then you see exactly like that diagram.
Okay.
Right? But the important thing is not where the contact. It's not really the contact. Direction are opposite. When you eventually draw the free body diagram, it's always a point object. Okay? Now, to give you some more thought about this, you have to realize that when you have this scenario, suppose you push on this box. All right? Now, the box 2 is in contact with box 1. When you push on box 2, it would push on box 1. What Newton's third law tells you is whatever force that is exerted by box 2 on box 1 exerts the same force back on box 2. Okay? So if this is the force exerted on box 1 by 2, then box 1 would exert a force on 2 in the opposite direction. They are equal and opposite. Now, that doesn't say that it doesn't matter which way you push. This contact force, this one, this pair of action-reaction pair, this contact force does depend on whether you're pushing this way or pushing this way. If you actually do the analysis and work it out, you would see it. Now, what do I mean by doing the analysis? Let me sketch it for you. What happened to my pen? Oh, the black one.
You're right.
Oh, okay. So if you look at the big box, I'm going to look at the smaller box and you apply a force F. Now, when I say analysis, I want to look at the contact force. This is what you do to figure it out. You draw what we call free body diagrams. All right. This is free body diagram for 2. what forces are acting on 2? You say that is the force that you apply, right? And 2 pushes on 1, what does 1 do? Pushes back in the opposite direction, right? So there is another force. Let me call that F. All right. Now when I draw, sometimes I don't draw vectors because I'm drawing magnitude and directions. Okay. Now these are the 2 horizontal forces. Newton's second law says sum Fx equal m times pi a sub x. What is the net x force? Look at this.
0.
Not necessarily. All you can say is this is minus F plus nil F is the mass of box 2 times by the acceleration of box 2. Okay? That's what you write down. Now, when you draw the free body diagram for box 1, the only horizontal force is that exerted on 1 by 2. Now, if this is F, what is this? It will have the same magnitude. You see, I already draw the direction, right? Opposite to this. So this would be F. Okay? And when I apply Newton's second law, when I do this, what is the positive direction? When I write down this equation, what is the positive direction? To the right. Right? That's why big F, which is pointing to the left, is negative. That's why this is negative and why this is positive. When I work this out, if A sub 2 is negative, what does it mean? It means it is accelerating in that direction. It's a magnitude and a direction. Okay? If I keep to the same convention, then what does this do? This says minus F is equal to mass of box 1 times by acceleration of box 1. Now, look at the thing, look at the 2 boxes. When I push on box 2 and the 2 move as 1, what can you say about the motion of box 1 and box 2? They are identical, right? What does that say about their velocities?
Equal.
Equal. What does that say about their acceleration?
Equal.
Equal. Therefore, I can call this A2 and A sub 1, but in reality, I know physically from the conditions they are the same. So I should not call them by different symbols when they are the same. Or if you want, mathematically, I say A1 is equal to A2. And I write that as A. And I go and change the equation. You can do that if you want. But that's just mathematics, right? Or I can just realize at the beginning that this one and this one has the same acceleration. Whatever it is, they will be the same. And this tells me that A is negative. Since I call to the right positive, I know that the acceleration is to the left. Okay. Now, look at this. If I work this out, I can put this as minus m1a, right? F is minus m1a. So I can put this in. And I can bring that to the other side, and I end up with minus F is equal to m1a plus m2a. I can factor out my a. Yes?
Wouldn't you be putting the negative F for the negative F1?
F1 is minus m1a, correct? From this equation.
Okay.
So I substitute for, not F1, sorry, F is minus m1a. So here F is minus m1a. I'm just substituting for little f there.
Right, it's just you have, I'm confused because you have the negative f equals m1a.
Right?
So then why are you switching it?
Because this is an f, not a negative f.
Divide both sides by -1.
What's that?
Divide both sides by -1, I guess.
Yeah, or if you want, I multiply both sides by -1. Then this becomes f, and this becomes minus m1a. Because this is f, right? If I want to replace f, I've got to know what f is. What this tells you is that if you look at this, you say, doesn't that look like one object of mass m1 plus m2 with a force capital F acting on it? The answer is yes. I told you before, what you call an object can be a composite object. So if I think of the two boxes as one object, what is its total mass? m1 plus m2. What is the force exerted on it? There's only F. You don't have those internal forces anymore, right? Because it's one whole body. You look at this whole body and you ask, what force is exerted on this whole body? There's only one horizontal force.
What about the direction? Is it always going to be positive or negative?
The direction of what?
Of big capital F.
That is dictated by the problem, right? If I tell you I have a box and I push to the left, that's the direction of F. Now, if you're asking whether that's positive or negative, I say you decide. You choose your coordinate system. If you choose to the right positive, then you would say F is negative. See, that's why I don't like it in that you really should understand this is a vector, and if you want to be consistent, you would write that as a vector. And if I write that as a vector, I would say the force is equal to minus F x hat. That's what I would do. This tells me that the magnitude is F, and the direction is a negative x direction, where the conventional x hat is the unit vector in the positive x direction. So without that, I resort to drawing diagrams, and then you have to understand implicitly this is the direction of the force. Okay? Yeah.
So the second scenario would be the one where the paper box would be crushed?
Yeah. What I'm trying to do here is what you find is that's why you do this analysis, and it seems long-winded and whatnot, but this is what you would do. You get A is minus F over M1 plus M2, and then you can write this, you say F is minus M1, A is F over M1 plus M2. Okay?
Can you write that somewhere else?
You solve for the contact force, you will get this value.
So we don't even need acceleration if we do that.
What do you mean? I did calculate the acceleration here. That's how I got that. It's just algebra. There are many ways by which you can arrive at the answer. You can solve for x, you can divide by this and get rid of a, and it never comes in. It's all up to you. It's a matter of algebra. The important point to note is the following, right? F is dependent on how hard you push, but also it depends on the ratio m1 over the total mass. The total mass is fixed. If m1 is large, F is large, right? Remember what little f is. Little f is the contact force. That's the force exerted, the action-reaction pair exerted between box 1 and 2. Yes, your question?
For the test, do you want us to explain it conceptually and solve it, or can we just solve it?
It depends on the question. Sometimes the question would require you to know it conceptually. You may not realize it, but if you don't recognize what it is conceptually, then you will set it up incorrectly. That's why I emphasize the concepts, because it's important. That's what ties all these things together. I don't emphasize the math because, it's tedious, but you can do it on your own time, right? Because you have done algebra, you've gone through all the exercises, you can do it. It may take you more time than I do, but you can do it. You have gone through it, you can do it. Trust me, you can do it. But setting it up is where the physics comes in. Yeah.
So you plug in your minus F into F to solve for the total force, right? Right there, that's that equation at the very top of that.
Yeah.
Minus F defines the total force, right? You found that's defined total force of the entire,
This is the force that is applied.
right?
Right. And little f is the contact force. Yeah, I have to break it up this way in order to get at the contact force. Otherwise, there's no way to get at the contact force. If I just look at the composite body, the contact force doesn't come in, so you don't get a chance to solve for it. So ultimately, you have to break it into two free body diagrams like this. Now, the point of all of this is the total mass, m1 plus m2, is fixed. And what I'm saying is that the contact force is larger the larger m1 is. All right? Now, I claim that that's what the mathematics show you. But your gut knows this. That's what I mentioned also, that part of the problem-solving strategy or skill that you can develop is to look at extremes. This is an example. What do I mean by extreme? I already told you. If you imagine this were a big boulder, heavy, big rock, and this is a paper box, a little paper box that you use origami and fold up into, right? And you put this here, and you put the little box against the boulder, and you push. What is the contact force? It is very large, because M1 is very, if you look at the equation, M1 is very large. So the contact force is very large enough to crush the box. Because that's what would happen when you push on the box. But if you apply big F on the boulder and push this way, what happens? The box just goes along for the ride. It doesn't feel anything. Because the contact force is very small, it doesn't get crushed. Okay. You know it, you don't, I hope you know it, right? If I ask you what would happen, would the box be crushed if I push on the boulder, you would know to say no. The mathematics shows you this is the case. That's what I mean by understanding nature. You're trying to understand what happens. And based on this analysis, and this analysis follows from what? Applying Newton's second law and Newton's third law. Right? I apply them correctly, and I tell you, this is my conclusion. And lo and behold, when you do the experiment, that is the case. So that's why I say sometimes it's difficult to understand this. This is an example of why I tell you people have difficulty conceptualize and accepting that when I have two objects colliding, if I have a big truck like this one and a small car, when they collide, you say, how is it possible? Look, the small little car is crushed. How is it possible that the force exerted by the truck on the little car is exactly equal to the force exerted by the little car on the truck? But if you actually analyze, you look at how the car moves. That is, before collision, it is moving with a certain velocity. After collision, it is moving with a different velocity. You look at the acceleration, you look at the forces, you do the same thing with the truck, and you find out that, yes, indeed, for them to move the way they do, the action-reaction pair are equal and opposite. you can do the same thing with a bug and the windshield of your car as you're driving, right? The car is coming along, the bug is flying this way, and when they meet, you all know what happens. What happens to the bug? It gets squashed, okay? The force exerted on it is large enough to squash it. And you might think, oh, the car must be the one doing exerting a large force, and the force exerted by the bug on the car is very small. The answer is no, that's not true. They are exactly the same amount. It's just that the mass of the car is so much larger than the mass of the bug. If you have the same force and the mass is very small, what does that mean about the acceleration? It's very large, right? F equals ma. Force equals mass times acceleration. If mass is very small, a must be very large compared to the car where m is very large and the resulting acceleration is minuscule. And that's what happens. You're traveling at 60 miles per hour, you suffer an acceleration. That is, you suffer a change in velocity. That's what acceleration is. But for the car, the acceleration is very small. So you go at 60 miles per hour and you suffer a small change. You drop from 60 to 60.999999. Do you feel that? No. But the bug suffers a huge change in acceleration. It goes from 2 miles per hour to 10,000 miles per hour the other direction. You see how big of a change that is? It's a very violent change. That's why it is. The action-reaction pair forces are always going to have the same magnitude. Okay, let me walk through this example. And it goes something like this, right? You hold a brick. So this is your hand. See how well I draw? And that's the brick. I can draw bricks very well. Okay, it's resting in your hand. And it says, how many forces act on the brick? Now look at the brick. So I'm going to draw the brick. In fact, I'm going to draw a free body diagram. So I represent the brick by a point. I ask, how many forces are acting on the brick? There's gravity. We call that weight. The force exerted by gravity on an object is the weight of the object. That's the force that's trying to pull the brick down to the earth, right? Why isn't it moving down? Why isn't it accelerated down? Because your hand is holding it up. So your hand is holding it up by exerting a force upwards. Okay? Now, those are the two forces acting. Now, question, identify these two forces. So there are two forces. That's the weight exerted by the Earth's gravity. That's the force exerted by your hand supporting the brick to prevent it from falling downwards. Okay? Now, they ask, are these two forces equal in magnitude and opposite in direction? Okay, we can apply Newton's second law. If the brick is stationary, what is A? Zero. Its velocity is not changing. From Newton's second law, sum of all forces is equal to, specifically, this is the y direction, right? Sum of f sub y equal m times a sub y, which is 0. Therefore, the net force must be 0. If you look at this free body diagram, these are the forces. What is the net force? It's F minus W. So F is equal to W. Now, no arrows, nothing. These are just magnitude. In order for me to look at the direction, what is the direction given by? By my drawing. I've got to look back to my drawing. Because I write this as F minus W based on my drawing. The direction of each force is already in the drawing. When I do this, I solve, I'm only solving for magnitude. When I go back and I want to know direction, I better look back at my drawing. Now, if I solve for this and I get, suppose I work everything and I get F is -3, and F is that way. What does it mean? It means that I originally drew the direction incorrectly. It should have been downwards. Okay, that's what the minus sign would mean when you actually work it out. Okay, now, so are these forces opposite? You drew it opposite. Are they equal in magnitude? Yes. So the answer is, are these forces equal in magnitude opposite? Yes. Are these forces an action and reaction pair? Why not?
Because they're not opposite.
Because it's on the same object.
They're on the same object. Remember, I told you the most important thing about action-reaction pair is they have to act on different objects. If they're on the same object, they are not going to be ever action-reaction pair. Okay? So this is somewhat of a trick question. Now, number 17 says, refer to the problem above. You are now accelerating the brick upwards. What changes in this? Do we still have two forces? Yes. What is the acceleration? Upwards. What is the acceleration value? We don't know. They didn't tell us. All they tell us is it's upwards. So we just call it A. A can be 1.2, 17, whatever number you like. See how easy it is? Whatever you like, you put it in there. It's just a number. A is just a placeholder for some number which you can put in as whatever you want. Okay? What changes? Well, you look at this and say, okay, I'm going to apply Newton's second law now, right? I have A going upwards. I still have the same equation, Newton's second law, in the y motion. That's what it means. I don't have to worry about x because it's very simple. Sum f sub x equal m times a sub x. What is sum of f sub x? 0. There's no x component anywhere. It's equal to m times by a sub x. So a sub x is 0. It's not changing its motion, its velocity in the x direction. Its motion is only in the y. Okay? All right. What does this give you? What this gives you is, I've called upwards positive. So F minus W is equal to mass times by the y component of acceleration, which is A. It's upward, so it's positive. That's all. I'm done. I have written this up, and it turns out that F is W plus MA. All this is saying is, are these forces equal in magnitude? No, F is larger. Are they opposite in direction? Yes. Are they action-reaction? No. Okay, simple enough. I have no time for this. I'll give you 1 minute to think about it. Hockey park slides on ice at constant velocity. What is the net force acting on the park? What? Net force equals 0. Why?
Velocity is equal 0,
So A is 0. Okay? If you apply Newton's second law, if A is 0, that's the net force. Net force is 0. Okay? Fairly simple question, as long as you look at it right. Now, this one is a little bit more, just a little bit more. You all have seen people climbing rope, right? You may not have done it. I've never done it in my life. But if you see someone climbing the rope, you can ask, when you climb up a rope, the first thing you do is pull down, right? You know you are going to pull down on it. Now, how do you manage to go up the rope by doing this? Why is it that by pulling down, you go up? Yes. The rope pulls you up. What do you attribute that to? Third law of action-reaction pair. What is your action? What's that? You pull down on the rope. So what does the rope say? You pull down on me, right? What am I going to do to you? I'm going to act in an opposite directions with the same force. So you pull down on me, I'm going to pull you up. And that is the force that is causing you to climb upwards. Okay? Now, I already went through this vector nature of forces. In 2 dimensions, what you do is this one, as I said, breaks up into one equation for the y component and one equation for the x component. That's all there is to it. And once you can do this, you can find the x component of acceleration, y component of acceleration, and then you quake, you sweat because you have to solve a lot of simultaneous equations, but you kick that off as algebra. Okay? As an example, like this one, what it does is you have 2 astronauts on a satellite and you are pushing in this direction. This astronaut pushes in this direction, this one pushes in this direction. So you can draw the figure, and the free body diagram, you basically represent the whole ensemble as a point, the satellite as a point like that, right? And then you put in the 2 forces. Presumably you're in space and there's no effects of gravity. So those are the 2 forces acting. Now when you talk about some fx, what do? You look at this and say, what is the x component of f1? It's just f1, whatever force is applied. What is the x component of f2? There you go. This is your right triangle. You go x and y. So this is the adjacent angle. It's cosine, it's positive. So f sub 2x is f2 cosine 52 degrees. And likewise, the y component is positive, and it will be f sub 2 sine 52 degrees. If I give you f2, they'll become numbers. If I don't give you f2, they're just algebraic quantities, and you just solve for them. Okay, and if you want to add them, this is how you add them, right? Vectorially, you draw head to tail, that's the total. Or if you want, you can look at the x component, which would be f2 cosine plus f1 magnitude. And then the y component is just f2 sine. Once you know the x and y components, you can find the magnitude and direction, if you want to find it. As I said before, all objects near the surface of the Earth, they fall with constant acceleration. Armed with that fact, you can now look at Newton's second law and you say, look, object that is falling, it has acceleration. What is the direction? Downwards. What's the magnitude? 9.81 meters per second squared. By Newton's second law, any object that is accelerated must be experiencing a net force. In this case, the only force, so the net force is the force. The force that is acting is what we call gravity. We give it a name. When physicists don't know anything, they give it a name. So that's gravity. Don't ask us what gravity is beyond this. It's much more difficult to try to. There are certain things that are fundamental, and what is fundamental depends on how deep you want to go. But at this level, that's just the force of gravity. All right, it's one of the fundamental forces of nature, and it is exerting a force downwards. So we write net force, which is the weight, equals mass times acceleration, which is g. This is a magnitude equation, and as usual, g is just a number, 9.81. Now, the last thing we want to talk about is something called normal force. Now, that's just another name. what is this normal force? The normal force is a contact force. Anytime you have contact between two objects, there will be a normal force. All right? Think of an apple sitting on the table. The apple is in contact with the table. There will be a normal force. Now, what do I mean by the normal force? That would be the force exerted on the apple by the table. Okay? The apple pushes down on the table pushes up on the apple. What do you mean by the normal force? That's the force that is perpendicular to the surface. Now, for a horizontal surface, the normal force on the apple is upwards. Okay? Now, when you tilt, imagine a table, I tilt it, and I put a brick on it. I tilt it ever so slightly, so very small tilt. What happens to the brick? From your experience, what happens to the brick? Okay, let me show you. This is a brick, right? This is my table. I'm going to tilt it ever so slightly. What happens? Nothing. Okay? And when there is no motion, there's no acceleration, I know the net force must be zero because A is zero. And you have to ask yourself, what forces are acting? Now, this is the table. This is getting ahead in some ways, but it illustrates the point. This is the tilted table. This is your brick. We know there is always a force of gravity. What is the direction of that force? Mass times acceleration, which is always straight down. I don't care how you tilt your table, gravity is a force straight down. Okay? Now, if A is to be zero, the net force must be zero. What must be the direction of the net force? If this doesn't accelerate, this is stationary. What must be the other forces acting on this object? It should be straight up of magnitude mg. Okay? This is not the normal force. By normal force, we mean the force exerted by the table on the object that is perpendicular to the surface. Now, this is the tilted table. What's the direction that's perpendicular to it? If you have difficulty understanding what perpendicular means, convert to Christianity and think of a cross. All right, so this is my cross. So I'm going to tilt it. You see? That's the perpendicular. Okay? This means this is, I didn't draw it perpendicular, but you know what I mean, right? That's 90 degrees. That is called the normal force. We represent that by the symbol capital N. So what this tells you is that there must be other forces acting so that the sum of those forces must equal to mg. All right, so these two forces are not sufficient. You all know what the other force is. I'm getting ahead of myself. This is chapter 6, but why doesn't it slide down? Because of friction, because the table is rough. There is yet another force. It's just that that force of friction plus this normal force must be equal to mg upwards. That's what we will conclude. Okay? So the normal force is just a force that is perpendicular. Now, this is another common mistake I find a lot of people make. And they always think that the normal force equals mg. And they arrive at that erroneous conclusion from this simple case where you have a horizontal table, you have a brick, and I ask, what forces are acting? You say, okay, free body diagram, I've got the weight, and I have the normal force. In this case, the normal force is straight upwards. Those are the only two forces acting, and when I say sums F equals 0, you get N minus mg equals 0, and you conclude that the normal force is equal to mg. Now, how did we arrive at that? We arrive at that by drawing the free body diagram and applying Newton's second law. Okay? Let me put another situation. Okay, so this is a brick, and I really dislike the brick. I despise it. I'm going to step on it. I'm going to step on it this way at an angle. So in other words, I'm pushing down on the brick with some force. This will have some angle theta and some magnitude F. If you don't like theta and F, just put down 10.2 newtons and 37.4 degrees. I don't care what they are. Okay? So I can now ask you, in this case, and much as I step on it, it doesn't move. And I now ask, what forces are acting on the brick? I'm going to draw the free body diagram, okay? And suppose I tell you, this is a rough floor. It's not moving, right? But whatever the case is, if I look at the free body diagram, I would say that is always the weight, mg, right? And because it is pushing down on the table pushes up with a normal force. Normal means perpendicular to the surface. If this is tilted, that's the direction of the normal force. It's no longer up, but tilted, right? You will get an opportunity to do those things later. But suppose you look at this and then say, look, I'm stepping on it. I am pushing down on it. I can draw the force this way. I can draw the force this way. It makes no difference. Okay? It doesn't matter whether you draw the force, that force that I'm stepping down on the brick with this way, or draw it this way. Typically, people draw it with all the tail starting at the point, but it really doesn't matter, okay? Now, if these are the only three forces acting, what would happen to this object? Suppose I tell you this is a smooth table. What do you think would happen to this object? It would accelerate in this direction. How do I know that? Because sum fx equal m sub ax. What is the x component of this? This one, non-zero. I add 0 to something else, it is always non-zero. Therefore, this cannot be 0. Therefore, this is some finite number. It will be accelerated in the negative x direction. Okay? Now, is it accelerated this way? This is a hard floor. I step on the brick, and then the brick just goes off. I have to continually step on it, though. Not a realistic situation, but that's what we do. So a constant force F. All right? Now, so you move to the left, right? You're accelerated to the left. What about this motion? What can you say about this motion? It's not moving up or down, right? It's not moving down because it's a hard floor and I'm not strong enough to stomp the brick through the floor. It's not moving up because it will be a strange world indeed where you have a brick and you step on it and you start moving upwards. Right? You know there's no motion, you know it's going to go to the left. So the conclusion is a sub y is 0 and a sub x is not 0, if this is a smooth floor. If I tell you a sub x is 0, that means there must be another force that cancels the x component of the applied force, so that the sum of f sub x is equal to 0. Right? But if I'm just interested in this one would tell me what? Sum Fy equal to M sub Ay would tell me right, A sub y is 0. And if I look at those are the three forces. I would say N minus mg minus, what is the y component of this? You see that it's negative. And this is the y is opposite, so it's sine. So you say it's minus f sine theta is equal to 0. The reason I write this down is because n is equal to can you see that n is not equal to mg? In fact, if you try to internalize it, you press down on the brick. All right? What happens to the normal force? The normal force is what the floor feels from all these things that are pushing down on it. Can you see that if you push down on the brick, the floor pushes harder upwards, right? So you expect the normal force to be larger than if you do not push down on the brick. If you do not push down on the brick, you know the normal force is mg. We worked that case out. So when you push down on it, the normal force becomes larger. So imagine what happens in this case when you're pulling on the suitcase. You're pulling upwards and moving the suitcase in the horizontal direction. What do you suppose would happen to the normal force? Would it be the same as mg, larger than mg, or less than mg? Everyone should sense that it's less. If you work it out, you draw the free body diagram, the only difference between these two problems is instead of stepping down on it, what am I doing? Pulling up. I do the same analysis and everything. I conclude A sub y is 0. I do exactly the same thing. You will find that now the y component is positive. And when you bring it over, it's negative. And you see that it is now smaller. Okay? Now I think that's about all there is. This is to tell you that it's always perpendicular and you can do this. And I don't have time to get to the questions. But you will see this again in chapter 6. So prepare for your exam on Tuesday by converting to your favorite religion and pray a lot. Yes.
What do we have to bring besides the green book?
Besides the what?
Green book and Scantron, that's what we bring, or what do we bring?
No scantrons needed, just your cheat sheet, your scientific calculator, and your pen and nothing else.